As you remember, last week, we've been talking about the energy analysis of closed system. And we took few questions, we solved few questions, but the major point we were focusing on is how to, the first thing is in closed system, we said that we use the delta U or the internal energy values that we can find from the, for example, from the property tables, such as the steam tables. And also at this stage, we don't have any other option. So if we, let's say, want to find the energy balance of any system, we have to add, as we said before, we have to add all the values of the work, input or exit from the system, and all the heat input and exit from the system, plus the change in internal energy, kinetic energy, and potential energy. Remember these system energy. And we said in regard to the internal energy, we can always refer to the property tables. And in the property tables, as you can see here, let's say in this one, we can always go to, for example, column 3, and you find U. Because in a closed system, we use only U, we don't use H. We don't have moving fluid, as we mentioned before. So we use U as internal energy. But in case that we don't have, let's say, U values or H values, if we have moving particles or moving fluid, we can get these values from the gas, ideal gas equation. And we said this is the, these are the two properties, the specific heat for at constant volume, CV, and specific heat at the constant volume, constant pressure, CP. Okay. So these two values, CV and CP, can be found from tables. And I will show you very soon how to get the value for H, value from CV, we can get the U value, and from CP, we can get the H value. So it's quite simple. So let's do it one by one and show you the options that you have. In case for example here, in this table, for example, gives ideal gas specific heats of various gases, common gases. And this is table A2. So in table A2, you have different subtables. The first one is the one that give you the CP and CV, specific heat at constant pressure, specific heat at constant volume for each gas. So for example, for air, for argon, for any other, let's say for oxygen, whatever gas you select, you can get the values of these CP and CVs. But this table is only calculate or give you the values of CP and CV at temperature, which is close to ambient temperature, 300 K. And the reason why showing this temperature, because if we go, let's say, to extreme temperature, Cp and Cv will change. Therefore, we have to find different value from tables for Cp and Cv. So let me show you what do I mean by this. For example, here in this graph, in this graph, you can see that there is the x-axis represents the temperature, and the y-axis represent the Cp value. So for temperature value, for any temperature, if you go, let's say, higher temperature, for example, take any gas, for gas CO2, starts with a certain value for Cp, and then with the temperature, with increase of the temperature, this value goes sharply to higher values. So the more temperature you get, the higher Cp value you get. But this is when we have extreme change in temperature. So we're talking about jumping from 1000 to 2000 K. But in most of the cases, or most of the examples we are dealing with, first of all, we are dealing with air, most of the examples in this course, and we always take air temperature close to the ambient temperature. What I mean that the difference, let's say, probably delta T is not more than 30 or 40, which would not affect too much the values of Cp and Cvs. But what I want to ask, what I want you to explain here or show you here is how to find the value of internal energy U and the value of H by using the Cp and Cv values. So again, as we know that the delta U, or change in temperature, is a function of specific heat. The delta to change in internal energy is a function of change in the delta Cv. And Cv, we said that for a certain range of temperature, we can take it as average value. So therefore, delta T, delta U value is the average value of the specific heat at constant volume multiplied by delta temperature for a certain process. Same thing for the enthalpy of ideal gas or liquid. If we know the Cv average, then the value of enthalpy, or the change in enthalpy, is simply Cp average multiplied by the change in temperature. All right. So as a conclusion, now we have actually three methods to determine the internal energy and enthalpy of an ideal gas. The first one, as we know, we had before, we can refer to the tables and find the enthalpy or internal energy of a certain gas from the table directly, as we did, let's say, with the steam or the refrigerant 134A. So we always we're using the tables. We just follow the temperature, which temperature we are working on and then take that temperature and then find the H and U values from the tables directly. If we don't have tables, which this is like happening sometimes, if you don't have tables to find H and U directly, then we can use the ideal gas equation, as I mentioned before. We have two equations for H, one of them for H in terms of Cp, and the other one U in terms of Cv. Okay, let's do some like quick example here. For example, if I have a temperature here for the air, So this is the first box, or the first table is for air. So for air, I'll take this table, and for example, at 300 K, which is about 28 Celsius, at 300 K, I can find the value of Cp. All right. If I multiply Cp times the temperature, I should get H based on this based on this equation. The first equation here says H is equal to specific heat multiplied by T. So specific heat is 1.00 multiplied by 300 will give you around, let's say, 301 kilojoule per kilogram. Okay, and this is actually the enthalpy. If I go to the tables, the one which is the one I had before, and let me check what's the enthalpy for air at 300. If I can get it from the table. So this table here, if I go down to 300 here, can you see it? And check what's the enthalpy, H, which is the same thing here. You can see that H is 300.15, which is similar to the equation value. So that shows that you can get the H value either from tables or from the ideal gas equation in terms of Cp and, or if we have internal energy, then in terms of Cv. Is there any question so far?
No, sir.
Okay, so this is the second one. So we said the first one from tables directly, we can find H and U, or you can get them from the equation in terms of Cp and Cv. Or the last one here, sorry, it's quite complicated actually. This is following a formula or a function given here in this table. This function actually will give you the Cp value in terms of kilojoule per kilomole Kelvin. We will not use this equation in our examples, but it's also good to know this because for future work or future research you have, if you don't get, or if you can't get the Cp value of a certain gas, you can always refer to this equation. And what happens here, in this equation actually it gives you values for constants. As you can see, it comes in Cp is equal to A plus B T plus C T squared plus D T to power 3. And A, B, C, D, all of them are constants. You can find these constants from the table here. So for a certain gas, for each constant it's shown here in the table, you can just refer to these columns and you can get the value of these constant for a certain gas, substitute them in this equation, and then you can get the value of Cp. Okay, any question before we move to the, so this is in brief, the last topic we didn't finish last week. So how to find the value of enthalpy or internal energy using ideal gas equation rather than going to the tables. Okay, any question?
No, sir.
Okay, thank you. Right, so then now we'll start the new topic. So today topic is mass and energy analysis of open system. Last week, we were talking about the closed system. And we said that closed system, we don't have, in the closed system, we don't have mass crossing the boundary of the system. And therefore, we have limited actual application in the real life for a closed system. Most of our analysis in real life, we have open system. We have flow going into the system and flow leaving the system. So let's find out what's the major topics we're gonna going through it. Today we will have mass and volume flow rate. We'll talk about this. What do we mean by mass flow rate and what do we mean by volume flow rate? And conservation of mass, because there's the law of conservation of mass. And also we will talk about the energy analysis of a system. What do you mean by the flow work or energy or the flowing fluid work? And also we will talk about energy analysis of any steady flow process. These are the major topics that we're going to focus on today. But before we start with this, just to give you a brief description about the open system. As I mentioned before, it's most of our real life systems are open systems, such as the one that you can see here in the left side. This is a system which is the represents domestic hot water system. It's a solar hot water system actually, and as you can see here, this side here, which is the collector or solar panel that heats the water, and the water is coming from this side, so it's coming to the system. So there is a flow of fluid crossing the boundary of the system and then going inside the solar collector, heated by the solar ray or solar radiation, and then takes this hot water to the tank. From the tank, there is other loop, which is the water loop of the house. So we have water coming from the mains and then heated by the tank, and then this water can be consumed inside the house. So there's a water flow in, water flow out. And this is actually, it's an open system, as you can see. Also, on a bigger scale, if I take a bigger scale system, which is the one to the right side, this is what we call a power plant or electric power plant. In this power plant, we convert the heat generated by burning the coal inside the furnace to electricity through a system, a complicated system, but this is like a very simple diagram representing the system. And as you can see here in this system, there is flow coming here, which is the fuel, the coal. The coal is taken to the a furnace, as you can see, burned inside the furnace. And inside the furnace, there is a loop of water tubes, high quality or pure water inside this loop. And then when the water gets heated, it's converted to steam. And then the steam can be taken to steam turbines to rotate the turbines. Then these turbines rotates a generator, as you can see here. And then, the generator here. And then the generator takes generates the electricity voltage increased to higher voltage, and then can be taken to the nearest power line or to be used by in the cities or in the industry. And also we can see here there is a cooling system. There is water coming from the lake or the river. This water cools the system inside the power plant. And when it gets heated by the exchanger here, we can take this water back to the river. So the warm water, we can take it back to the river. Instead, we can take the cold water to cool the system. So again, you can see that we have so many inputs and exits from the system. But what we are trying to explain here, that this is an open system because we have fluid flowing across the system in many parts of the system, such as, you know, the cooling, the water, the river water, we have, let's say, the gases coming from the chimney. So we have gases coming from the burning the coal, and this is crossing also the boundary of the system. So we have fluid in, fluid out. So this is an open system at the end. So this is in brief, what do we mean by open system? There are so many other systems. For example, this is a gas turbine, which we use this kind of turbines in, for example, for in aeroplanes or any other system that require jet engines. Also, this is a traditional vehicle engine, such as the petrol engine or diesel engine. Same thing, we have gases entering the engine from this side and gases exit the engine from the other side, which means that we have fluid crossing the boundary, and this is an open system again. Do you have any question regarding these examples? Please feel free to ask. All right. Okay, so we'll go back to the theory that we want to present here in this lecture about the mass and volume flow. Remember, we said that we're gonna talk about the conservation of mass, the law of conservation of mass. And mass and volume flow, I think we mentioned this before. We talk about how to find the mass flow rate and volume flow rates in any system, but it's good to repeat it again here. We talked before about the velocity, average velocity in a system, and we said that we use the average velocity because in an internal flow, in a tube or a duct, the flow has different velocities. The velocity at the middle of the flow is higher than the velocity adjacent to the wall of the tube. And we said at that time because there is a viscosity or friction force between the fluid and the walls. This friction reduces the velocity of the fluid and brings it like close to zero, while the maximum velocity we can expect is somewhere in the middle of the tube. And therefore we said, in order to find the mass flow rate, we need to get the average velocity between these two velocities. And as you can see here, the mass flow rate is integration of the rho v dAc, because when you move away from the center, the velocity also change. Therefore, if I do the integration, I will end up with this general equation of mass flow rate. So now, from now, you need to remember this. Mass flow rate is equal to density multiplied by average velocity multiplied by AC. So what's AC? May I ask you here? Can someone tell me in this, let's say, example, what do you mean by AC?
Area, sir?
Cross-sectional area.
Cross-sectional area.
Correct. So sectional, let's say, for example, for this tube, the sectional area, if I look at it from this side, from side view for this tube, the sectional area of this is simply, it's a circle. So this is a circle like this one here. And if I know the diameter of the circle, then I can find the area of the circle, which is AC, which is the area of the cross-sectional area of the tube. So correct. Okay, now we know how to find the mass flow rate inside a duct or a tube or a pipe. And volume flow rate, actually, it's quite similar. It is the average velocity multiplied by area. So in mass flow rate, we add the density, which is rho, while in V dot, which is the volume flow rate, we have only velocity multiplied by AC. So it's really quite simple. So just remember these two, please. The mass flow rate is density multiplied by average velocity multiplied by AC, and volume flow rate is AC or average velocity multiplied by AC. Okay?
The volume flow rate is this small v, and the velocity is bigger v.
Volume flow rate, actually, you can see here, V dot. There is dot on the top of the V. So we call this volume flow rate. Okay.
Oh, thank you, sir. I thought it's a differentiation. That's right.
Yeah. No, yeah. That's. But when you see the there is a symbol like this in the book. There is a dash above V. This shows that it's average velocity or velocity. Just to differentiate this from the mass flow rate of volume flow rate. Sorry. Okay. So it's better to differentiate them by this. So if you could put a wave dash on the top of the V, this represents the velocity. If it's V dot, there's dot on the top of V, this is volume flow rate. Okay.
Okay, sir. Thank you.
Okay. So now let's show you what we mean by conservation of mass. So in these two examples, let's say we have this bathtub, and if I have flow rate from the tube here, from the tap going inside the bathtub, and the flow rate here is 50 kilogram. In the meantime, there is a drain from the tub leaving the water leaving the tub to the drain. Okay, if the coming mass equals to the leaving mass of water, then the level of water inside the tub will remain constant. There is no change in the level of the water inside the tub. But if the mass, for example, entering the tub is more than the mass leaving the tub, then we can find that there is rise in water level with the time, because we have more water coming than water leaving. So we call this kind of balance we call it mass or conservation of mass, or mass conservation. Okay, so we follow this equation actually. The mass entering the control volume of a system during a certain time, delta T, this is delta T represent time, minus total mass leaving the control volume during the same time, should equal or must equal the net change in mass within the control volume during the same time, which means that if I have here 5 kilogram entering the system, and we have also again 5 kilogram leaving the system at a certain time, what will be the change in mass?
Should be 0.
Will be 0 because there is no change in the mass of the system. Correct. So there is 0 kilogram. So we call this conservation of mass. It's quite really simple.
So delta T is the difference of temperature?
No, delta T is a period of time. I'm saying here, let's say 5 kilogram per second. This is a delta T in second. So in each second, I have 5 kilogram entering the system, and I have same time. We have the same time. Right. Sorry. Yeah. If I have 5 kilogram per delta T, which is delta T here per unit time. Okay. So let's say 5 kilogram per second entering the system. And I have also on the other side, we have 5 kilogram during 1 second leaving the system. So delta T here, it represents a period of time. Okay. Right. So any other question? All right. And you also can see this example. This is like a case where we have 2 inputs and 1 exit. So we have such type of systems, many applications. For example, we have here, let's say we have an airflow, 2 kilogram per second of airflow. And in the meantime, we have another fluid. For example, we have fuel or gas. We want to burn the gas. So we have 2 kilogram per second, for example, of gas, and 3 kilogram per second of air. These 2 fluids combined here in a combustion, for example, and we have a reaction. We do a combustion, and then these 2 fluid after combustion will leave the system as gases, combustion gases. So the total mass of the gases leaving the system must equal the mass of the gas plus the mass of air. So which means that we have to add 2 plus 3 to give us the total value of exit gases, which is 5 kilogram per second. It's just a very normal balance. You balance the exit with the inlet. So whatever inlet you have to add them all to these inlets should equal the exits from the system. Okay. Any question? Okay. We have in open system, we have another definition, which is the in some systems we use fluid, for example, as a gas, because remember when we say fluid, it we mean either a gas or a liquid. So in a gas, if we have a liquid such as, let's say, water, the water, you can compress it. If you put a water inside the cylinder cylinder or piston and put water inside the cylinder or piston system and try to compress the water, the volume will not change because water doesn't change the density easily like with the pressure. So therefore, the higher pressure, you get almost similar volume of the water. Therefore, we said water is incompressible flow or incompressible fluid. And for incompressible fluid, we call the system a pump, such as this figure here. This is a pump, and we use the pump for incompressible liquids or fluids. And there is always inlet to the pump, V1, and there is also exit, V.2. So there's a volume flow rate entering the system must equal the volume flow rate leaving the system. And therefore, we can simplify this by this equation, summation of all V dot, the volume flow rate, must equal summation of all exit volume flow rates of a system. This relates to the mass conservation. So we call this steady incompressible flow as a single stream. And we can put it in terms of the definition of V dot. So V dot, we said before, it's average velocity multiplied by area should equal the average velocity at the exit multiplied by the area at the exit. All right, so not necessarily the area, the inlet area is equal to the exit area. You will find later on that in many systems, there are differences between the area, inlet area and exit area. It depends on the type of system. So therefore, each side has different values for area and different values for velocity. Because if you change the area, the velocity will be changed to keep the balance same. Okay. So now this is for compressible fluid. We have also, incompressible fluid. We have also compressible fluids, such as all types of gases. If you put a gas inside a cylinder and a piston system and try to compress the gas, you can easily compress it because you can change the volume of the gas inside the cylinder by compressing or by moving the piston. Therefore, we call this compressible fluid. And in compressible fluid system, we don't use pumps, we use compressors. So we need to differentiate between pumps and compressors. If you have, let's say in the future, you don't say compressing the water. Is this right to say compressing the water in a compressor?
No.
Why is no?
It's a fluid.
Yeah, it's liquid. The water is a liquid and it's incompressible. So you can't say compressing the water, it's pumping the water. So pumping means the liquid is incompressible and you are using the pump. While in a gas, if you go, let's say if you go to a petrol station, you need to increase the pressure of the car tires, then you use a compressor. So you said the compressed air and the compressor here, because the air is compressible fluid. And therefore we use a compressor rather than using a pump. We don't say pumping air, it's compressing air. Actually, this is the scientific term for the system or the process. And then, therefore, air compressor here, again, follows the same theory of the mass conservation. The mass entering the system must equal the mass leaving the system. So as you can see here, we have m.2 kilogram per second, m.2, same thing, m.1, 1 is kilogram entering the system is equal to the mass flow rate mass leaving the system, because it's a mass conservation. While because it's compressible fluid, you find that V1 is different from V2. The volume flow rate is different because here the density for a gas is changing in a compressor. Therefore, you will find that the volume flow rate will be different. Okay. Okay, let's have a quick example just to nourish your knowledge here. We have, for example, this is a system where we use a device which we call a nozzle. And a nozzle is a device that, it's a tube actually, or a pipe, has different diameters. The inlet diameter here, which we call it, say, A1, or the inlet area, cross-sectional area, is bigger than the exit area, A2. And if we have such pipe or such tube, then if we are applying the mass conservation, in the mass conservation, we said we should have the same flow rate. So m dot 1 must equal to m dot 2, correct? This is the mass conservation. Now, what's the equation of m dot? Remember, we said rho, density, multiplied by the area, multiplied by the velocity. So rho V1 equals same thing. If we assume that density doesn't change too much, we can say 1 if you like, 1 and 2, multiplied by area 2, multiplied by the velocity at the exit. Okay, and because the area here is bigger than the area at 2, therefore, to keep the balance or to keep the equation balance, the velocity here must be higher to keep the balance the same, or keep both sides equal to each other. And therefore, you'll find that in such type of system, we have V2 is bigger, much bigger than V1, the velocity at the inlet. And we use this phenomena in the jet engines or in the rockets, because we need thrust force, and the thrust depends on the velocity. So the higher velocity we get, the more thrust, or the more, let's say, pushing force to the rocket. So that's an application for this kind of devices, which depends, or which relates to energy conservation, or mass conservation law. Okay, so in this system here, we have, as you can see, a nozzle at an air entering the nozzle with a density 1. So let's say density R here, rho, is equal to, what's the density here entering? So 2.2.
2.21.
Correct. Kilogram per second. Okay, and we have velocity also, V1, also given here. So the V1 is 40 meter per second. Okay. And the density leaving is
Sorry.
also,
Excuse me, sir. That
Yes.
rho is 2.21 kilogram per meter cube, right?
yeah, yeah, oh, sorry, yeah, correct. Thank you. It's really good. Thank you. So kilogram per meter cube. Thank you. And the density leaving the nozzle, 7.62. So 0.762 kilogram per cubic meter. And also, what else? Do you have any other information here?
Velocity, 180 meter per second.
Yeah, correct. So velocity V2. We have 180. You can see like the velocity, it's at the exit is much higher than the inlet. The inlet was 40, while in the exit was 180. So you can tell that this is because of the nozzle design, okay? Because of the change of the diameter or change of the area of the nozzle. We have other information given here, which is the, the area of the nozzle. So we have area at the inlet. If there's any question? So we have area 1 also given, but this is in centimeter. Please make sure that you do the conversion in the exam. So centimeter square. Okay, so we have all the information here given. We want to find the mass flow rate. Let me ask you a question here. Does the mass flow rate here at the exit is different from the mass flow rate at the inlet? What do you think? Elias? Christopher?
I guess, sir, it should be different, sir, because the nozzle has got the different diameter.
But do we have, how many input and output we have for the nozzle? How many inputs?
It's one input and one output.
Okay, so based on
I
the
think so, because it's air, so it's going to be same because of the air.
well, if it's air or liquid, both types of fluid, whether it's air or liquid, because we have only one input and one exit from the system, and based on the mass conservation, the mass flow rate must equal. So whether it's air or it's liquid, you have always the same mass flow rate. Just make sure that you remember this. Whether it's liquid or gas, you must have the same mass flow rate. So mass flow rate entering the system must equal the mass flow rate leaving the system. Okay, so when the question here asks you to find the mass flow rate through the nozzle, you can find it either at the exit or at the inlet, doesn't matter. Okay, so you just need to check which part you have enough information for your equation. Remember the mass flow rate equation, m dot is how to find it. It's density multiplied by velocity multiplied by area. So you check which side you have all this information.
The inlet?
Inlet, correct. Because inlet we have the area, we have density, we have velocity. So I can substitute these three values, I can find m dot. And this m dot 1 must equal m dot 2. Okay, so if I find it for 1, it's also for 2. Okay.
So the mass flow rate is going to be same either for gas or liquid.
Yes.
When it comes to volume, then
Volume
it would be
no,
different.
correct.
When we use air.
Yeah, exactly. When you use air, the volume flow rate will be different because the area is different from in both sides. Yes, correct.
So for fluid, mass and volume going to be same all the time, but only for the air it could be different.
No, just put it this way. Mass flow rate is the same for liquid and gas.
Okay.
Okay. Volume flow rate will change if it's gas.
But when it's fluid, it's going to be same.
The same, yeah, because the density of the fluid will be almost the same. But for the gas, will change. So if the density change, the volume flow rate will also change. Okay, so just remember this. Mass flow rate is same for gas and or liquid in the system, but in a volume flow rate, you need to check if it's a gas. If the area is different, then definitely volume flow rate will be different. Okay. Okay, good. So now, how can you find, please, the mass flow rate through the nozzle from this information? Just make sure that you are substituting the right units. So if I want to take the density of the inlet, we said density of the inlet is 2.21. This is kilogram per cubic meter. Okay, what else?
And the velocity,
Yeah, velocity is 40.
40 meter per second.
Correct.
And then the area is 90 centimeter cube, but we're going to convert it into meter.
Yes, so if it's 90 centimeter cube, centimeter square, divided by how many centimeter in a meter?
I think we're going to divide it by 1,000.
100, but its square should be 10,000.
10,000. Yep.
Yeah. So now you can find the mass flow rate. Okay. Just please calculate it and find out the mass flow rate.
So it's going to be 0.7956.
Okay.
Sorry, again,
0.795 kg per meter.
Yeah, kilogram per second. Correct? Mass flow rate. Correct?
Yeah, it's second. Yep.
Because we're gonna delete all these meters from all sides. We have only kilogram per second remaining. Correct?
Yep, that's correct, sir.
And this mass flow rate must equal to mass flow rate 2, because we said it's always constant based on conservation of mass. And mass, now if we want to find the area at the exit, I know the density 0.762 multiplied by the velocity is 180 multiplied by the area, which is unknown. Okay, so area here can be found, area 2. I can take the same value for mass flow rate. So I can say 0.795 divided by 0.762 multiplied by 180. Right? And you can get the area at the exit. Okay, what's the area at the exit here?
0.00.
So
0.0085.
0085. But this is in meter, correct?
Oh, yeah, so for mine is 0.00579.
Oh, really? So
58.
different.
58, not 80.
58? Oh, okay. Yeah. Okay. Thank you. So it should be 58 then. 58. Yeah. Thank you. So this is the area. If they ask you in the question the diameter at the exit, you can do it, right? Because it's a circle, I can say the area is pi d squared over 4, sorry. and I can find the D value, the diameter of the pipe at the exit. Yeah? Because if I find the area, I can find the D. Correct?
Yes, sir. Yep.
Yeah, so this is a very quick, simple example, but show you the application of mass conservation law. Any question before I clean the page? Okay. Okay, thank you. All right, so, okay, time now is 11:30. Okay, we still have time, good. Now, we come to another topic in this lecture. It's the flow work and the energy of a flowing fluid. As you remember before, we mentioned in the closed system, we were using the internal energy because we don't have, we said there is, in most of the cases in a closed system, there is no flowing fluid. But in an open system, as you have seen in the previous examples and figures I showed you before, the flow is crossing the system. There is a flowing fluid. And in order to make the fluid flows, we have to apply work. So the fluid requires work to move it from one side to other side. And therefore, we have to add another term to the energy equation. This term, we call it flow work term. Okay, so then the flow work term, we have this the flow work term will be based on the definition of the work. We know that the work is the force multiplied by the distance. In this case, we have the force F, which is the force required to push a certain amount of fluid across or push it in a distance L. So if I multiply F by L, I can get the work required to for the flow or the flow work. So this is can be found by these equations. So we can say F here is simply the force is pressure multiplied by the area, and then if I substitute the area here, the pressure, I take this part A and L, which is the area multiplied by the distance, will give me the volume. So I can reduce the work equation to a PV equation. So work is equal to pressure multiplied by the volume. Okay. Now, this is the equation of the work of a certain or a flow work of a fluid. I can add it to the energy equation, and as you can see very soon, this can be reduced to enthalpy. So this is the energy equation we mentioned before for a closed system or any system actually, total energy of non-flowing fluid. And then if I add to it the PV, then PV and U will give me enthalpy. So here in the equation here, I changed the U value to H value because I have added the PV value. So remember we mentioned before, H is equal to U plus PV, right? And because I have added the PV in this equation to the internal energy, I can replace it with H. So now I have the new equation for the flowing or fluid or open system equation, which has the H value rather than the U value. Okay, so the total energy of flowing fluid of mass, we can multiply it by of mass m dot, we can multiply it by m dot. So this is per kilogram. If I multiply the equation by m dot, I can give this in kilojoule per kilogram. Sorry, kilojoule per second. Okay, because m dot is kilogram per second, multiplied by kilojoule per kilogram, give me kilojoule per second. Okay. Any question? Okay, now let's summarize this now. For any system, okay, the energy, the total energy of a system is represented by this equation. Okay, so from now on, you don't say U plus V squared by 2 plus GZ, you say H, because we have added the flowing work or fluid flow work of the fluid. Okay, so for open system, this is the equation that we need to use now. Okay, for open system, the total energy of an open system is H plus V squared by 2 plus GZ. In a closed system, we use U, not H, plus V squared over 2 plus GZ. Okay, and we're gonna come very soon to the total to the energy balance of a system. In energy balance, of course, we need to add the work and the Q. Okay, let's do some practice, because I believe that it's become too complicated now. Too many informations has been added. So let's take this question, and I'll explain to you this question now, and then we go to the Kahoot. We try to solve it step by step. Okay, so in this question, we have a pressure cooker. I think we used this before as we talked about the pressure cooker, and we said, what do we mean by pressure cooker? So in a pressure cooker, the operating pressure is given here, which is 150 kilopascal, which is higher than the atmospheric pressure. Can someone give me like an approximation? What's the atmospheric pressure in kilopascal? Any idea, or can you remember this? Any one of you? Peter, William, sorry?
1000.
1000 what?
1001?
1001, I mean, what's the units here?
The atmospheric kilopascal?
Yeah, but 1000, it's big, too big.
I think it's 1.0325.
Yeah. 101, correct, 101 kilopascal.
Oh, sorry, yes.
Yeah?
It should be Pascal if I...
Yes, correct. So if it's atmospheric pressure, it's around 101 kilopascal. Now we have 150. So we have about 50 kilopascal higher than the atmospheric pressure. Okay, so we have the pressure given here, and the question said that we know the volume. Actually, volume is 4 liter. So we know that it's 4 liter. We can convert it to cubic meter. And in the question, they said that the amount of liquid in the cooker has decreased by 0.3 liter in 40 minutes. Okay, so we know that 0.6 liter of the 4 liter has been removed from the liquid. Okay, so the amount of liquid in the cooker has decreased by 0.6 liter, which means that some of the steam is leaving from the cooker because of this valve. There's a valve at the top, and some of the steam is leaving. So this will affect the level of the water or liquid water in the cooker. Okay, so we know now 0.6 in 40 meter. So we know the mass flow rate. The mass flow rate from the cooker. If I have the volume flow rate 0.6 liter, this is the volume. This volume left in 40 minutes. So I can say V dot, which is the volume flow rate. What's the equation of the volume flow rate? We said that it's velocity times the area. Okay, and this V dot, which is V1, okay, I can say V dot is equal to, we know that's 0.6 liter. 0.6 liter divided by 1,000 to change it to meter. All right, and in how many, what's the time?
40 minutes.
40 minutes. So 40 minutes divided by 40, but should change the minutes to seconds, correct?
Yeah,
Because,
divided by 60.
Yeah, times 60.
Oh yeah, times 60.
Okay, now I can get the volume flow rate in cubic meter per second. Okay, so now if I get the volume flow rate, all right, I can find the area. The area is already also given here. Exiting area is 8 millimeter square. Also, I have to change to meter. So if I have the mass flow rate and I have the area, I can get the unknown, which is the velocity, the equation. All right. So that's one. The total and flow energy of the steam per unit mass. So let's do this first. Do first part, and then we come to the second part, which is the flow energy. We completed after the Kahoot. But at this stage, is it clear for everyone? Any
Yes, sir.
question? Okay, before we move to the Kahoot application. All right. As you know, the Kahoot is the time where we can exercise what we learned so far, and also I will record the attendance during this, because this is we will consider the attendance. Whoever joined the Kahoot, I will put him as attending the class. So please try to interact and join the Kahoot now. Let me open the exercise. Okay, can you please enter the Kahoot? I'll take the attendance while you are doing this.
So what's the code?
Sorry. Yeah.
Sir,
Yes,
I cannot access to Kahoot game.
you can't.
Yeah, I think the connection lost. Yeah.
Oh, okay, now I think it's come back. Yeah, I think there's a problem in my internet connection.
Yeah,
So
yeah.
now it's, I think it's now it's coming.
Yeah, yeah.
right?
Yeah, I logged in. Yeah.
Yeah, this is like, sometimes the internet is not working well.
Excuse me, so I don't know how to enter this thing.
You haven't done it before?
No.
So you
I
just,
think so.
yeah, go to the Kahoot, just write Kahoot. And then it will ask you to log in or enter code game pin. Do you have any other student has a problem with entering the Kahoot?
Yes, sir. It says mine's reconnecting.
Okay. Let me check. It's really bad in the internet.
So is it the Kahoot internet or what?
Sorry?
Is it the Kahoot internet? Is it like down or something?
No. So you can't access it?
I can. I'm in there, but it says it's reconnecting. Like the connection's been lost to Kahoot.
Yeah, maybe if your internet,
Okay.
your internet connection is not performing well. Try please again.
It's back, sir. It just took a
Back?
while.
Okay, yeah. Well, same thing with my place. I have a slow internet, so we will wait for everyone. Okay, so Elias.
Yep.
Are you in, Elias?
Yeah.
Okay, thank you. Muhammad, address? No?
No, sir. I don't know why. I can't do it.
Sorry.
Is it possible, like, so you can?
Okay, can
Not
someone, yeah, if I go, let me check here, because I'm not a student, but I'll check now if I can. So if we write Kahoot like this, and here, enter game pin here. Can you see this?
Yeah, I can see it. So what's the pin?
So pin is this one here, 4565402.
No, it's saying internet connection problem. No.
Sorry? Pandal?
Yes, I'm in. I think
You're
so.
in?
Yep.
Okay, so your name, Pandal?
No, it's Mohammed Idris.
Mohammed Idris, okay. So you are in, Mohammed?
Yep.
Okay, good.
So I haven't done this thing before.
Oh, okay, no, that's good. So this is good practice now. You know how to do it, right?
But
So
I can see, like,
you
have
just joined the class today, this week? Because I
no,
couldn't see your name before.
I have done it before as well.
No, I mean, this is the first time you come to this class?
No.
So your name was here before, right? But I couldn't see your name before. It's all absent.
Because I never actually logged into this Kahoot thing.
No, but I mean, I'm talking about this is the first time you come to my class, right?
No.
So then why you are absent? Shows absent in other weeks.
If I'm logged into into the Zoom thing, so I should be present, right? I don't know, sir. I think so. I have missed
No,
this thing.
because what I was using, guys, was calling names in the previous weeks.
But
And
that's all right. That's fine. I have
yeah.
attended the previous week.
I couldn't say your name anyway.
But that's
so
all right. Okay.
today you are here, week 5 now. So Ahmed Bakhtiar. Ahmed Bakhtiar is not there. Okay, Abdulaziz is there.
Yes, doctor.
Faisal is there, right?
Yes, sir.
Bandar is not there. Jungshi.
Yes, sir.
Jungshi, yes, thank you. William is there.
Oh, yes.
Thank you. Mervin.
Yeah, I'm here.
Thank you. Tariq, Malik Tariq. Malik Tariq. Yeah.
Hello.
Imran.
Yes, sir.
Okay. Asif. Asif is not there. Neo.
Yes, sir.
Neo. Yes. What is your name in the Kahoot? I can't see your name. Oh,
N-A-Y?
sorry.
Yes, Nay.
I can't see it in the Kahoot.
Oh, really? I just already in, like, my name is Nay, N-A-Y.
Can you see here? This is the Kahoot page. I can't see your name here.
Oh, no. I'll try it again.
Yes, please. Yeah. So Chris.
Yeah.
Yeah, thank you. And Pandal.
Yeah. Yes, sir.
Pandal, where is your name here?
Pandalemon's my full name and it's Peter for short.
Peter.
Yeah.
All right,
Yeah.
thank you. All
Yeah.
right. Because I just need to know this.
Yeah, all good.
So let me put, yes, sorry. I'll put in brackets Peter here just in case I.
Yeah.
Okay.
And so it says I've been absent since week 1. I've been here every lecture.
Really?
Yeah.
Maybe because that's how I was checking your name. I couldn't find Peter. Okay.
Oh, okay.
Okay, I'll check it now. I'll go back to my record and put.
Okay.
Okay,
Yep.
no worries. Thank you.
Of course.
Okay, thanks everyone. Let's start now. Everyone is in. Okay, so I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 students. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 is, I believe, Neo. Neo is not there, still not joining us. Okay, Neo there. Who is not in yet? Is one not in with us? Can you check your name on this screen, please? On the Kahoot screen. If you don't find your name, please.
There's 14 participants in the Zoom.
4, 5, 6, 7, 8, 9, 10, 11. No, 14 because I'm 2. I have two devices.
Oh,
Okay. So 14, then it means we need more 2. Can you please put your name again? Elias there.
Yep.
Idris is there. Idris, you're not there.
So I just logged out of there.
Yeah, please join because I'm gonna take your attendance based on this Kahoot. All right, log in now. Otherwise, you'll be absent. Ready? Elias, sorry, Idris. Okay. All right, so I'm going to start now.
It says my name is taken, or I don't know what's wrong with it.
Just re-enter the code again, please.
Okay.
Okay, so this is the question again. We mentioned we have 4-liter pressure cooker and we have the pressure 150. You need to go to the steam tables, saturation steam tables, table A4 or A5, and at 150, pressure 150, find what's the specific volume of liquid. So I need to find VF from tables, table A5. Okay. So we have 7 correct. So you just go to the table and find at the pressure 150, what's the VF specific volume at that pressure, straightforward. Okay. So Elias, good. Question 2, if we have 0.5 liter of liquid in 40 minutes, what's the mass of the liquid if VF is given? So we know the VF, and you know that the mass of the liquid. So VF right, correct. So we have the volume 0.6. The amount of liquid has decreased by 0.6 liter in 40 minutes. What's the mass of liquid if V is given? So we just need to divide the liter 0.6 by the 1000, because this is in meter, and then divide by the specific volume. Okay.
Excuse me, sir, if you don't mind, can you check I'm in there or not?
Check your name.
Yep.
I think because we'll see now. Are you in?
I don't know, sir. I don't know how to check it. I don't know.
Okay, all right. We'll check later on because we already started, so we cannot go back. Okay, we'll see now at the end. All right. Question 3. If the amount of liquid in the cooker has decreased by 0.6, same thing, but now we need the mass flow rate. So the mass flow rate we said, put it in terms of the VF. Good, thank you. So we know that, yeah, the the mass flow rate is given. Sorry, this is, we have 0.6 liter in 40 minutes. You just simply divide the mass here, because you know the mass, and then divide by the time, you guys get mass flow rate. Sorry, the volume flow rate. Okay, and then from previous answer, you have VF, you can get the mass flow rate. Okay. Okay, so next question. Now we know the area, exit area. We have the steam flow rate, we know it. We have the V gas, because you know, this is saturated gas here. When it leaves the cooker, it leaves as a gas, a saturated gas. So we need to find VG. So VG is already given. Just apply the mass flow rate equation. Yeah, good. Okay, if you have any question, please ask, because as I said, we are practicing now, trying to understand different formulas, how to find the values from these formulas. Okay. Number 5, what's the total energy equation? Sorry, the total energy equation is simply you need to find out which one of these is applicable. The first one, second one, third one, or fourth one. If you don't have work, then you can ignore it. If you don't have the potential energy, then you can ignore it. See which one is of these applicable. Correct. The first one is the right one, because in the first one, we have only change in velocity and also change in enthalpy, because we said a flow crossing the system. But we don't have work. That's why we ignore this one. We ignore this one also. We don't have work, and we don't have potential energy. So the one that we have chosen is the first one, the correct one. Yeah. Okay. Right, so the last one, last question. What's the flow energy PV of the exit steam? So we need to find out PV. And remember, if you know the enthalpy, and you can find H, you can find PV, sorry. So PV is H minus U. So you need to find the H gas. And U gas. And the difference will give you PV. Yeah, I know it's, you need to go to tables, steam tables, but this is just to give you an idea. We're going to go back to the question and solve all these things, but this is just to give you an idea how to find the flow energy, which is the PV. You find the HG from the tables, you minus this from the UG from tables, because at the exit of the cooker, the steam is saturated steam. It's not liquid anymore, it's steam, but saturated steam. So we can find HG and UG, and then the difference is give you PV, which is the the 173.9. Okay. Thank you. Okay, any questions so far? So the result now. So, I think she's second, and the first is Peter. All right. Thank you, everyone. That's really good. Your contribution is really appreciated. Okay, so we'll go back to our question. All right, so back to the question here. Remember, we found the mass flow rate. So we already found the mass flow rate from this equation. And remember, we said delta V, we know the amount of fluid leaving the cooker, which is 0.6 liter, they said here in the question, 0.6 liter in 40 minutes. So we found the amount of the liquid decreased, which is 0.57 kilogram. And then if you want to find mass flow rate, you simply divide this by the time, which is 40 minutes. But of course, we need to change the units to seconds. Then you can get in second kilogram per second. Also, we found the velocity, because the velocity also required here in the first part of the question, exit velocity. So exit velocity is, we can use the mass flow rate equation. So now we know the mass flow rate divided by the density of the gas, divided by the area at the exit, which is also given, 8 millimeters square. Substitute these values, you can get the velocity at the exit. Okay. And now to find the flow energy, the fluid, or the flow energy of the fluid, or flow work, we said that you need to find H value and U value from tables. And then you substitute the value, you can get the PV. PV represents the flow energy of the fluid. Okay. Now, the total energy which should include the potential plus kinetic plus enthalpy. Because potential energy is zero, we only have H and KE. And you can see now the difference between the KE is very small. So let's take this here. I'll show you here. This is the KE, the kinetic energy. The kinetic energy is 0.588 kilojoule per kilogram, while the enthalpy itself, the enthalpy by itself is 2,693. So 0.5 is almost nothing compared with the 2,600. So that's why it's not, the kinetic energy is not affecting too much in this system, but the energy equation, we should include it because we have enthalpy and we have also kinetic energy, but we don't have potential energy. Okay. And then the last section, the total, the rate of at which energy is leaving the cooker, you simply multiply it by m dot. So we know the m dot, the mass flow rate, you multiply it by the total energy, which is this one here, the enthalpy one. So if you multiply this by the mass flow rate, you can get the energy rate or the energy in kilojoule per second or kilowatt. Okay. Any question? Okay. All right. So we go back. We go to the energy analysis. Energy analysis of steady flow system. And when we say steady flow system, just remember, please, when we say steady flow, there is no change with the time. So the properties of the system doesn't change with the time. Therefore, we call it steady flow system. So they say the mass flow rate will not change during the time. The temperature inside the system will not change during the time for a certain point, and so on. So all the properties will remain constant with the time. Okay. So for this type of system, as you can see, we have a flow of fluid entering the system and fluid leaving the system. All right. In this kind of system, if you want to apply energy equation, so the mass balance, we know it, all the mass flow rate inlet should equal to the mass flow rate at the exit, correct? And also, if you apply the energy balance, remember the energy balance we mentioned before, a few previous lectures, we said that energy balance for steady flow system, the rate of net energy transfer by heat, work, and mass, which is this part, must equal the rate of change in internal kinetic, potential, and potential energies. Okay, this side, the left side should equal the right side. Okay, and if there is no change in internal energy, then we should equal it to 0. Now, this is the general energy equation or conservation equation. And we end up, if this side, right side is 0, then we can end up with this formula. Rate of net energy transfer in heat, work, and mass must equal the exit rate of energy transfer by heat, work, and mass. Okay, now this is the final shape of the equation. Okay, so this is the final equation, energy equation or conservation equation of the system. As you can see, we have the input heat, input work, plus the total energy input to the system must equal exit heat, exit work, plus summation of all internal energy exiting the system. All right, and this is the general equation. If you have more than input heat, you can add it to the same equation. If you have more than exit heat, same thing. If you have more than exit work, you do the same thing. So all the Q values and all the W values, you have to add them in your equation. Whether if it's input or exit, you have to include them in the equation. So if it's exit, you put it in the right side of the equation. If it's input, you put it to the left side of the equation. So you add these energies, all of them, you add them together and to maintain the balance of the energy equation. Okay. Okay, so what's the application of this kind? I just want you to remember this, please. Try to remember this equation and use it from now on. Whenever you have a system, you write down this equation and then you eliminate the terms that you don't want or you don't have it in your system. I will show you how to do it very soon. But just remember this now for the time being, and then we'll come to it very soon. Right. Let's apply this to different type of systems. So the energy balance or energy equation or conservation equation. We'll take this device. We already had an example on this device, which is the nozzle. We said that the nozzle can be used in different applications, such as the application of the jet engines or the rockets to get higher thrust from the engine. And if I apply the equation here, this is the energy equation, the same one we mentioned before. So we should put all the terms and then eliminate the one that we don't use or it's not applicable. So for example here, do we have heat if it's an isolated device? Do we have any Q dot in or out from the system?
No.
No, correct? So we can eliminate both sides here. Right. What about W for this type of system? Do we have shaft work, like we have a shaft taking work from the system or input work to the system?
No.
No, correct? So we can remove this also, these two terms. If I say take the input and I exit, are they in different level? Like is there Z between them, like difference in height? So the potential energy apparently has no effect because the level is the same, inlet and exit. So then we can eliminate this GZ, correct? So you can see that we have reduced the equation to m dot summation of m dot h I plus v square over 2 equals to summation of exit mass flow rate multiplied by H exit plus V squared divided by 2. So I make this equation simpler. Reduce this equation to this new equation, and then I can add the values if I have it, and then solve it for the unknown. Okay, this is the way that you apply energy equation for any system. So this is one case. All right, and we have the same thing. You know, the nozzle, as you can see, we said in the nozzle, the area at the inlet is bigger than the area at the exit. There is other device opposite to the nozzle. We call it diffuser. Diffuser, we have the area here, inlet is smaller than the area at the exit. Is it the opposite way? And why we need this device? Sometimes we need high pressure at the exit. So if you want high pressure at the exit, you use the diffuser. If you want high velocity at the exit, then we use the nozzle. Okay. So the diffuser, same thing. You apply the equation here and start to find out what are the terms that not applicable, and you remove them from the equation and reduce it to a simple form of this equation. Is it clear for everyone? Please ask now.
Yes, sir. Could you please give us an example of the diffuser?
Diffuser, okay, good, thank you. So can you see this, this airplane engine down here?
Yeah.
This is an airplane engine, and as you can see, the part, this part, the inlet part is a diffuser, where we want high pressure entering the engine. So the air under high pressure with the fuel will join together, mix together in a combustion chamber to produce heat. The amount of heat with high pressure will rotate the turbine. So you need high pressure to make more energy to rotate the turbines of the engine. And that's why we are using diffuser at the inlet. While at the exit, can you see the exit here? This is the exit of the engine, the left side. Can you see them?
Yeah.
So the exit, as you can see, it's a nozzle because the exit part is smaller area than the inlet. And in the nozzle, at the exit, now we need thrust. At the inlet, we were seeking the pressure to make combustion and make energy to rotate the turbine. At the exit, we want now thrust to push the airplane forward. Yeah. So this is an application for these two devices in one system. So we have diffuser in the turbine, and we have nozzle also in the turbine, gas turbine of the plane. Is it clear for you?
Yep, sir. Well, it's the only thing I'm confused. It says diffuser is a device that increases the pressure of a fluid.
Yeah.
But it's not a fluid, right?
No, fluid. I mean, I said before, fluid, it's for a gas or liquid, doesn't matter. So when we say fluid, we are mentioning a gas or a fluid or a liquid. So in this case, we have gas, we don't have fluid. We don't have liquid.
Okay. Thank you.
So that's why we call it a fluid. But sometimes we use a diffuser, let's say for liquids. For example, we have a pump and we need high pressure from the pump. We use a diffuser. So we are pumping water under high pressure. We need a diffuser at the end, not a nozzle. Yeah. So this is the difference. But in general, we say fluid because we may use this diffuser for a liquid or a gas, no matter. Okay. So another application, the turbines here, we mentioned this now. So as you can see here, who was asking this question? Sorry, Imran, or who was asking the question about the diffuser?
It's Idris and not me.
Idris. Oh, okay, Idris. Yeah. So this is another example of the diffuser in one system. As you can see here, the inlet, we have bigger area, smaller area, and the exit is, this case is bigger area, while at the exit of the turbine, we have opposite way. We have nozzle design. So that's why we have different application for the nozzle and the diesel and the diffuser. Okay. What else here? As you can see here, there's a compressor. We said before, we compress air, we compress the gases, and this is another way to apply the energy equation. You can apply the energy equation, but in this case, let's say, for example, as you can see in the compressor, in order to rotate the compressor, if I want to rotate the compressor like this, I need work, correct? So I need work, and therefore work inlet must be in the equation. We can remove it from the equation because we have work in. So this is part of the energy equation, not like the previous examples. And work out, we don't have work out because we don't produce work from the compressor. While in the turbine, if you can see here, this is the turbine equation. In the turbine equation, we produce work from the turbine. So if you look at the turbine work is, we are generating actually work from the turbine. That's why actually we use turbine. So there is work here. So work exit. So therefore I cannot remove the Q out. I must keep it. But there is no Q work input, so I can remove work input. If there is no heat exiting the system, then I should keep, sorry, this is the work, and Q out. If there is Q out, then I should keep Q out. If there is Q in, also I should keep Q in, and so on. But if there is no, let's say, change in Z, I can remove the Z. This is the way that you can reduce the energy equation to a simple form of the equation so that you can solve it easily. All right. Any question here? All right, so this is an example on the energy equation. This is a really a general equation and a general example, and this is really very common because it relates to the steam turbine, and steam turbine is a very popular system or device in power plant, as you mentioned, as I mentioned before at the beginning of the lecture. In the power plant, we produce steam, and the steam can be directed to steam turbines to produce work, and then this work can be used to rotate generators and then produce electricity. So this is a good example for us to practice. For this type of example, we have all the information given for the inlet, we have all the information given for the exit, and we know how much power we are producing from the turbine. Okay, now the question here asks us to compare the magnitude of delta H, delta Q, delta KE, kinetic energy, and delta PE, potential energy. We need to find out, is there a big difference between them, or some of them very small, we can ignore them in the future or not. So if you want to start solving this, as you can see, we need to find the enthalpy. The enthalpy at the inlet here, we need to find H1, but also we need to find H2. Because this is the important property here, as enthalpy is the key factor in energy equation. So to find H1, as you can see, the steam is at high temperature and pressure. And if you go to the tables, you will find this steam at this pressure and temperature is in the superheated region. And therefore, we have to use the table A6. Okay, so A6, table A6, if you use A6 and select the 2 megapascal pressure, at this pressure and temperature, you can find the enthalpy, H1. Okay, so this is the inlet enthalpy. The exit enthalpy, as you can see, it's not completely a gas. Why it's not completely a gas? Can someone tell me why I can see, like I say, here, it's not completely a gas at the exit? There's a property here. If I have it, it gives me a clue that there is a mixture here, not a complete phase or one phase. Yeah, Imran?
Sir, yes.
Yeah. How do I know that the exit is two-phase? Any one of you?
X equals 90%.
Jiangxi, yes, thank you. Jiangxi, thanks, Jiangxi. Jiangxi said we have this X value, which is we said steam equality. Remember this? Whenever you have X, means that you have two-phase region. And therefore, you need to use the equation of the two-phase region. And remember, this equation, I'll show you here again. The equation of the two-phase region is, for example, for H for two-phase is equal to, I can find it from HF, if I know HF, which is from tables, plus the X value I have, times the difference between gas and fluid enthalpy, so HFG. This is also can be we can get it from tables. So if I put this in the equation, I can find the two-phase value of the enthalpy or the exit enthalpy, H2. Okay, so this is what actually we did here in the second step. We substitute the values using the X and then find H. Now, delta H between the inlet and exit, this is what we have. Delta H giving me this value. While delta KE, can you see here? Delta KE is only 14. And delta PE even less. Can you see delta potential is 0.04. It's almost zero. So this tells us that it's no need to include delta PE because it's very small. It's 0.04 kilojoule compared with the delta H, which is 885. This is really nothing. So that's why we can exclude delta PE from our calculation because it's too small. Right? Any question? I'll finish because I think some of you would like to leave very soon. So just do this quickly. So the other part is determine the work done unit mass of the steam flow through the turbine. So you need just to find out the energy equation But this is the, actually, we know the work here, so we don't have to apply the energy equation because we're already given this power. So if you have the power, kilojoule per second, what you need to do is actually, if I know the, again, if I know the energy equation, if I know the energy equation, I can get the work per kilogram. So apply the energy equation that I mentioned before, remember? And we said we remove the parts or the term that not applicable. So which part you think from this equation I have removed? Can you see this equation? Which one I have removed? From the
Heat transfer, sir?
Yeah, correct. I have removed the Qin because there is no Q transfer to the steam turbine, and there is no Q out leaving the turbine. And also, what else? There is one thing else.
Row density?
No, we have here
WN.
Yeah, correct. WN. There is no work in.
But the thing is, if we have like even one of these quantities, we have to keep the other one, right?
Sorry, again, say it.
Like if we have W in or W out, we have to keep the whole equation.
Yeah, but we don't have W out, so we can remove
So it's going to be 0.
Yeah, exactly. Yeah, we
Okay.
can. So it's 0, actually. You can keep it, but put it as 0. That's fine. But yeah, this is the final form of the equation. All right, so we add all these terms together and then you find the work per kilogram. Now I know the kilojoule per kilogram. I know the total power, which is 5,000 kilojoule given in the question. If I divide the power by kilojoule per kilogram, it gives me the flow rate, the mass flow rate. Okay, and that's how to find the mass flow rate if you know the power output. All right. I hope this is like, give you some clarification to the energy equation and how to apply it to different systems. But yeah, if you need more details, you can always ask or send me an email, or you can also, tomorrow in the tutorial class, you can ask Dr. Ahmed. He will be happy to help you. So we leave this for next week. We have a question here about heat exchanger. You're going to use this type of question or this type of application in your lab report. So in the lab, you will have an experiment on heat exchanger, which is kind of this similar to this this example. So we'll go through this example next week, and yeah, if you have any question, please let me know. All right. Any question before we leave, guys?
Thank you.
Yes, sir. I have a question, sir. If
Yes,
we don't
yes.
log in into this Kahoot thing, so you're going to mark us present or absent?
No, if you don't join the Kahoot, I will put you as absent.
No, because today I was unable to.
Yeah, okay. I will today. You have different case, but please next time try to join the class before we start the quiz or start the Kahoot. Because
Okay,
once we started, you can't join anymore.
Okay, thank you.
Okay, Mohammed. Any other question, guys? All right. Stay safe, guys, and we'll see you next week. Thank you.